This is Fundamental Problem 24 from Chapter 15. In Fundamental Problem 24, two identical 10-kilogram spheres are attached to the light rigid rod, which rotates in the horizontal plane centered at pin O. If the spheres are subjected to tangential forces of 10 newtons and the rod is subjected to a couple moment of 8 times t, where t is in seconds, determine the speed of the spheres at the instant t is equal to 4 seconds. The system starts from rest. Neglect the size of the spheres. So we have the force P acting downwards on this sphere and upwards on this sphere. The spheres are at a distance of 0.5 from pin O, and we have our couple moment here. The mass of the spheres are the same, so they're both equal to 10 kilograms, so I'm just going to call that m, little m, for both the spheres. So now take a look at your equation sheet. So we have equation 15-18. This is the initial angular momentum. The angular momentum is the vector r going to A from O, crossed with the mass times the velocity of A. Now we have a sphere on each side, so for the total angular momentum that's coming from both of the spheres, let's write this down. The angular momentum about point O is equal to the vector r going to point A from O, crossed with the mass times the velocity of A. We need the initial angular momentum. Well, the initial angular momentum is equal to 0 because the system is starting from rest, so the velocity is equal to 0. For the final angular momentum, this is the angular momentum from both of the masses. You're going to get the same thing for each mass, so it's just twice what it is for one of the masses. The vector r is going from O to your mass, so it's either pointing like this or pointing like this. In both cases, that's perpendicular to the direction of the velocity. So the velocity would be like this or like this. So in both of those cases, doing the cross product is going to give you something in the positive k-hat direction. So this is the vector r, which has a magnitude of 0.5 times the mass, which is 10, times my final velocity, which is what I'm looking for. So that's my final angular momentum for the two spheres. And then going back to equation 15-18, you're going to do the sum of all the moments and integrate it with respect to t. So for the force P acting on this sphere and also on this sphere, you would do the vector r going from O to the sphere crossed with the force. So for the sum of the moments, again, just like for the angular momentum, it's going to be the same for each one. Your force is pointing up. The vector r is pointing like this, so the force is pointing in the same direction as the velocity, so that those are going to be in the k-hat direction. I guess we should have put the k-hat here. Okay, and I have two of them again, so my moment is the position vector of 0.5 crossed with the net, well, the force, P. So that's times 10. So that's for this force P and this force P, and I also have, when I sum up all the moments, to include the couple moment, which is 8 times T. Now I can use equation 15-18 and say the initial angular momentum plus the integral of the sum of the moments with respect to t is equal to the final angular momentum. So putting that all together, I have an initial angular momentum of 0. Then I have to integrate what I have here. So the system's starting from rest when t is equal to 0. I want to know the speed at 4 seconds. And I have 2 times 0.5 times 10. That's just 10. Plus the couple moment of 8t integrated with respect to t is equal to 2 times 0.5 times 10, which is again just 10, times v. This is the speed, not the velocity. So if you want to do like we did last time and say the magnitude of the velocity, you can, or you can just call it v. So now we go ahead and integrate. This 10 is constant, so when I integrate this, I just get 10 times t. When I integrate the second term, I get 8 times t squared divided by 2. Then I put in my limits of integration going from 0 to 4. That's equal to 10 times v. So putting in my limits of integration, 10 times 4 gives me 40. Then I have 8 divided by 2, which is 4. Then putting in the 4 here, that's 4 squared. So that's 4 squared times 4, which is 64. And that's equal to 10 times v. So v is equal to 104 divided by 10, which is 10.4. This is meters per second. And that concludes problem 24. So this was similar to the last problem that we looked at. All the cross products that we did, the vectors were perpendicular to each other. Here we had to sum up all the moments that we had. And so that was the moment from force P acting on each sphere and also the couple moment. And because we had angular momentum from each sphere, we had to include both of those in our final angular momentum. So that's it for problem 24.